All right, this is AP Calculus AB Section A, Unit 3, Lesson 3, Limits Involving Infinity. Last couple of lessons we introduced the concept of a limit. And a couple of things I want to remind you of about limits. Number one, limits don't care what the function value is at the target. So the limit as x approaches c, we don't care what f of c is. We only care what the function does around c, both before it and after it. When we take limits involving infinity, there's two main cases here. One where the output goes off to infinity, and one where the x value itself goes off to infinity, either positive or negative. So let's take this example here. I'm going to say f of x equals 1 over x minus 3. 1 over x minus 3. And let's just analyze what this function is going to do in and around the value 3. So I'm going to take the limit as x approaches 3 of 1 over x minus 3. Okay, and we're going to use the table approach first, and then we're going to look at it graphically. So let's bring up Desmos. Not des least, but Desmost. All right, so let's put in our y. Our y function here is going to be 1 divide x1 minus 3. Okay, and let's put in some values close to 3. How about 2.9? Get negative 10, 2.99, negative 100, 2.999, negative 1,000, 2.9999, negative 10,000, 2.99999. Negative 100,000. What seems to be happening is this number is going negative very fast, right? It's growing exponentially. It's multiplying by a factor of 10 every time I add another 9 onto the 2. And so we can say that the limit as x approaches 3 from the left side, from below, seems to be negative infinity. Right? Seems to be negative infinity. It seems to go off just getting bigger and bigger and bigger without bound, right? And let's look at the same function, the limit as x approaches 3 from the right side, from slightly bigger than 3. Okay, and let's do the same thing. So here we go. Let's just start down here. 3.1, 10, 3.11. Right? 9.9099, right? And we're approaching 3. Oh, 3, I was going to say 3 point, it should be 3.01. 3.01, because that's not closer. 3.01. 3.001. 3.0001. 3.00001. By the way, if I put in 3, I get undefined. Why? Think about it for a moment. Hopefully you answer that if I put in 3, the denominator becomes 0, and we cannot divide by 0. So the function is undefined. Once again, though, 3.000001, this number seems to be growing, but it's growing in the positive direction, right? It's growing to positive infinity. And so since both limits are different, one goes off to negative infinity, one goes off to positive infinity, we would say the limit, the two-sided limit, as x approaches 3 from both sides of 1 over x minus 3 does not exist. Does not exist. Okay? Now let's examine it graphically and see if we can figure out what's going on here. Okay? Let's just get rid of that here. And then we're going to graph y equals 1 over x minus 3. Okay? And you can see there is this vertical asymptote going on. It's called an asymptote, 1s, A-S-Y-M-P-T-O-T-E, asymptote. And it's a line that nobody wants to cross, neither from the left nor the right. We keep approaching it, but we never get there. So if I graph x equals 3, that line, that green line is my asymptote. Right? It is a line that the function touches but never, 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 ever crosses. Okay? And vertical asymptotes are one of the types of infinite limits that go off to infinity. They don't always split in opposite directions. For example, what if I said 1 over x minus 3 squared? Let me do that here. If I put the quantity of the denominator squared, I would in fact have them both going up positive. And so in this case, the limit as x approaches 3 would be positive infinity. The two-sided limit would be positive infinity. Okay. Now I want to deal with the case where x goes off to infinity, either positive or negative. Okay, positive or negative infinity. And let's deal with that here. So here we go. I'm going to use this rational function here. I'm going to say y equals, or f of x equals, keep function notation here. Let's say x plus 1, x minus 4 over x plus 1. Yeah, let's do that. And let's take the limit as x approaches positive infinity of this function of f of x. Okay? The limit as x approaches positive infinity. So I'm going to do this a couple of ways. First of all, I'm going to go ahead and multiply this thing out. This is x squared minus 3x minus 4. And this is x plus 1. Okay? So this is the limit as x approaches infinity of x squared minus 3x minus 4 over x plus 1. So the first trick I'm going to use, I'm going to use a more formal approach. Notice the highest power on the numerator or the denominator of this rational function is x squared. So I'm going to do something. I'm going to multiply both sides by something. I'm going to multiply both sides by 1 over x squared. Okay? Which is just dividing by x squared. You could say that. I'm just dividing by x squared, and that's perfectly fine. Watch what happens when I do this. X squared times 1 over x squared is 1. We eliminate the x squared altogether. 3x times 1 over x squared is minus 3 over x. Okay? Negative 4 times 1 over x squared is minus 4 over x squared. And x times 1 over x squared is 1 over x. And let's see. 1 times 1 over x squared is 1 over x squared. So plus 1 over x squared. Okay? And so we're talking about the limit as x approaches infinity of these. Okay? So let's put the limit back in there where it belongs. The limit as x approaches infinity. X approaches infinity. All right. So here we go. Let's see. Let's look at just one part of it. What happens to 3 over x as x goes off to infinity? As the denominator of a fraction gets bigger and bigger and bigger and bigger, the fraction itself gets smaller. Because remember what the fraction says. The top number tells me how many. The bottom tells me how many pieces the whole is divided into. So if I took a pizza pie and divided it into 100,000 pieces and gave you 3 pieces, you would get very small, very little pizza, right? And the bigger that denominator is, the more pieces I cut the whole pizza into, the smaller each piece becomes. So this literally goes off, the whole thing goes off to 0. Anything over x, anytime the power of x in the denominator is bigger than the power of x in the numerator, it goes off to 0. So 3 over x goes to nothing. 4 over x squared goes to nothing. 1 over x goes to nothing. And 1 over x squared goes to nothing. So this literally goes to 1 over 0, which is undefined. But imagine as the number gets closer to 0. This happens asymptotically, right? So if I said 0 plus a little something, I'll call it epsilon, and then I said 0 minus a little something, a little tiny something, I would get a very large infinite number, positive infinite number, and here I would get a very large negative infinite number. So just like our first example, this goes off to positive and negative infinity, and the limit does not exist. Okay? It does not exist. Now, as x goes off to positive infinity, as x goes off to positive infinity, it's going to go off to the positive root, not the negative root. Okay? So it's going to go off to positive infinity because we're dealing with positive denominators. All right, and so this goes off to infinity, and let's check it by graphing it and see if that's really the case. Okay, so we have x minus y equals x plus 1 times x minus 4, all divided by x plus 1. Okay. And lo and behold, as we go off to infinity, this is a linear function, right? With actually a hole at -1, right about here, right here, undefined. And it's a linear function. As we go off to the right, it goes off to positive infinity. As we go off to the left, it goes to negative infinity, right? And the same thing is true. The same thing is true if I went off to negative infinity. I would still consider the same thing. Negative infinity, this term is going to go off to negative infinity, and or negative 0, right? A negative number slightly less than 0, and we're going to end up with a positive divided by a negative for negative infinity. Okay, so to the left, the limit is negative infinity. All right, so let's look at one where the limit actually does exist. And I know I'm going long, so I'm going to try to be efficient about this here. Okay, let's say I'm doing this. I'm doing the limit as x approaches infinity of x squared minus 5x plus 7 over 2x squared minus 3x plus 4. Okay, same step. I'm going to divide or multiply. I'm going to multiply both top and bottom by 1 over x squared, by the highest power of x. Okay, and we end up with x squared over x squared is 1, minus 5x over x squared is minus 5 over x, plus 7 over x squared, over 2x squared over x squared is 2, minus 3x over x is minus 3 over x, minus 4 over x squared, or plus 4 over x squared. And anything where we have x or x squared in the denominator is going to go off to 0, the limit, as x approaches infinity. As the denominator goes to infinity, the fraction goes to 0. 0, 0, 0. And this limit is 1/2. 1/2. Okay? And in fact, if I check the graph here, I think that's what we're going to find here. So we've got y equals x squared minus 5x plus 7 all over 2x squared minus 3x plus 4. Okay, there's our graph, and the asymptote, or the limit as x approaches infinity, is 1/2. Y equals 1/2. Okay, and lo and behold, looking at it, it seems to be that the further I go to the right, the closer and closer I get to that number. The further I go to the left, the closer and closer I get to that number. And as we go off to negative infinity, all those zeros are still 0, and we still have positive 1/2. So the limit as x approaches infinity is 1/2, and the limit as x approaches negative infinity is also 1/2. 1/2. So this is said to have a horizontal asymptote of y equals 1/2. Now, that said, there is a shorter way to do this, and I do want to present that. And I know I'm going along here, so I'm going to try to be efficient. Here's the way you can think about it. Consider only the positive terms in the polynomial expressions. Okay? As x gets infinitely large, it's going to matter less and less and less that I added 7. As 7 plus 200 million hardly makes a drop in the bucket. Same thing with 4, right? So the rest of it's going to grow so fast that the 7 and the 4 are practically nothing in comparison. Same with the 3x. The 3x grows in a linear fashion. The x squared grows in an exponential fashion, or a power fashion. And the x squared is going to grow a lot faster than the 3x. And so as x gets really, really big, the 3x isn't going to matter much. Neither is this 3x, because the 2x squared is going to grow. And so really this behaves just as the highest powers of x, x squared over 2x squared, and the x squareds cancel, leaving 1/2. All right, so that's another way to think of it. I like the top method for its formality. We can definitely demonstrate that it goes to 1/2, but you can also evaluate it in your head this way as well. Hopefully that helps.